Swayam Prabha. Digital India. Educated India.
And we have seen the boundary layer thickness from here, and then friction factor from here. So these two are important things to know for flow over a flat plate. Okay. With that, let us do some simple again practice questions to make sure that we have understood these things. Consider this turbulent boundary layer over a flat plate in a parallel flow. So which of the following is or are not true? It's asking for not true. So flow is still laminar in the region very close to the plate surface. We have seen it earlier. Okay. Flow is nowhere laminar in the boundary layer. Now let's say please note that we are talking about turbulent boundary layer, and then the thickness of laminar region decreases with the turbulent boundary layer. You can have in the turbulent boundary layer, the thickness of laminar region decreases or increases. You know from the discussions we had, and then the thickness of boundary layer, turbulent boundary layer, increases with x as you move, from leading edge to trailing edge in the plate. As you move along x, what happens to this boundary layer thickness for turbulent flow? Turbulent boundary layer, you can know that flow is turbulent in the boundary layer. Okay. Then the second question is the wall shear stress. That means shear stress at this surface is larger for turbulent boundary layer because velocity gradient is much larger close to the plate, very close to the plate. Larger for turbulent boundary layer because velocity is much larger close to the plate. We are comparing this to laminar boundary layer, and the wall shear stress is smaller for turbulent boundary layer because velocity gradient is much larger close to the plate. So and similarly, if it is smaller because velocity is smaller. So it's similar, but you find one right choice from there. This is just again as usual, it's a simple problem. Okay. So with this question, we'll now talk about flow around particles. So we were earlier looking at this flow over flat plate. We'll now look at flow around particles. So to before we start there, let us build it up on some simple situations. So let us consider spherical particle, for simplicity, or any particle. Let's say it's moving up in a fluid. There may be a container with liquid, or it can be something floating in air, or okay. So if it is moving up, okay, it's moving up at certain acceleration, then you can write the MA should be what are the forces acting on. There will be buoyancy, and of course gravity will be there, and the particle will interact with the fluid through some sort of boundary layer formation, etc. That happened here, and similarly it will happen in this case. And that some term has to be associated with friction factor. We call it drag, and the drag acts in a direction opposite to the motion of particle. Typically, there are cases where it can have same direction as well, but for a symmetric particle, if it's not rotating, etc. In this discussion, we can assume that typically it acts in the direction opposite to motion of particle. So since in this case particle is going up, so drag will act down. Okay, so we can write MA should be equal to buoyancy. Let's call FB minus F gravity, or mg. You can write So you can write F buoyancy minus mg minus whatever force drag. Okay. Similarly, if this particle is moving down, then you of course have gravity. You of course again have buoyancy, and since it is going down on the upward direction, you will have drag. So now we can write ma equals mg, mg are in the same direction, minus f buoyancy minus drag. Okay. So now let's say when particle just starts moving up, in this case, there is no drag if the velocity is 0. So fb must be greater than mg. Now as you are increasing the drag velocity, then the drag will also increase. Right? So if the drag increases, then at certain point this will become 0. Drag keeps increasing. Okay. Right. So similarly here you will have this. In this case also, initially mg is greater than fb. That is why it is going down. And as you increase velocity, this drag increases. So this will also become, at certain point it will become 0. So you will have net force equals 0 after some time, and so acceleration has to be 0. So that means you will reach to a constant velocity, which we call as terminal velocity. Right? So typically in such situation, there will be some terminal velocity that will be reached, and you may want to calculate that. And in order to calculate that, you should know drag, and we know that is a function of velocity. We'll look at it later. Okay. So now we have seen, for external flow, we saw the flow over flat plate, and in that flat plate we saw that it forms some sort of boundary layer here. This suddenly starts increasing. Boundary layer here, and then that is because of the interaction of this liquid with the solid. This is one type of interaction where flow is parallel to the surface. It acts as, there is some interference to flow, but it is because of this film formation or so. So that is typically known as friction drag, where we have friction, relative motion between these surfaces. So you have some friction drag. Now instead of this surface being parallel to the flow, what if it was perpendicular to the flow? So what you will have is, it will have some flow will come. It will most of it will be stopped, and then you go that. Some flow will come, stop, and then it will form probably a film, but then you will have some, it can't go anywhere, so it will have some separation effect. So flow separates, and it forms some kind of recirculation, what is typically known as wake formation. You may have seen such a wake formation, for example, if close to the boat, the sailors, you can see when they sail, there is close to the paddle, there is some wake formation, and close to pillars in river bridges, you will see wake formation and so on. So there's some wake formation that happens, and now this surface is obstructing the flow in a different way than this case. In this case, you didn't have any flow separation. You could have flow separation, but we didn't consider those cases here. So in this case, you don't have any. In this case, you have flow separation, and then you can see that there is some normal forces that is contributing to or obstructing the flow, and so these cases are known as there is another drag that is due to pressure. This is known as pressure drag. Okay. There could be other cases. Let's say if you have a spherical shape, or it could be a cylinder. So in such cases, you have this the flow comes. It actually floats flow around the surface. It follows the surface, and then depending on flow conditions, it can form the wake. So let's say it forms a wake, something like this. In this region, it forms wake. Okay, so you have flow like that, and so on. Okay, so in this case, you have the contribution to drag will be from both friction plus pressure. So you have two type of drag, and depending on situation, one type of drag may be more than the other. Okay. So in this case, if the flow is very slow, you for example may not form any wake, and then it will be mostly from friction. There is no pressure. So pressure drag is a very strong function of this wake formation. So it is important where does your flow separate from the surface. If it separates later, then this wake region will be small. If it separates earlier, then wake region will be large. So contribution from pressure drag will be more if the wake region is large. Okay. So now will Stokes flow actually deals with flow when you have very fluid velocity is very small, or so to say Reynolds number is very small, so that the flow comes, and of course this will stop, but others just go like this, but there is no separation of sort of thing. Okay, it is of course has to be symmetrical, and so it's very gentle flow. In these cases, there is the Stokes derived the equation and considered the contribution from both friction term and friction drag and pressure drag, and they found that the total drag is 6 pi mu r v. Okay. So then typically we have been even for flow over flat plate we talked about friction factor. So in this case, friction factor of course is then defined as d by a divided by half rho v infinity squared. So where your area in this case is projected area. So for a sphere, it will be pi square. Okay. So from here you can if you substitute all the 6 pi mu r v into 2, this 2 comes here, and then you will have pi r square rho v infinity square. Here also it's v infinity. So if you do all these things, pi cancels out, this r cancels out, this v cancels out, and then you have some 12 mu rho v infinity r. So if you convert this into d, this will become 24 by d. So for Stokes flow, which is essentially true for RE less than Reynolds number less than 0.1, where RED is again defined as infinity d by mu, but it's a fairly accurate till Reynolds number equal to 1. See, okay. So for this kind of flow, you can also calculate the terminal velocity. Terminal velocity also you can calculate, and I will leave that is an exercise. So let's say if the part this is flowing up, then your acceleration is of course 0. Gravity is down, but your buoyancy is up. You can write the terms for buoyancy. Then gravity is down, so you can write mg. And then your drag is down, so you can write 6 pi mu r, and v will be your v terminal. So you can find v terminal. Okay. So you can calculate this comes some 2 by 9 times density difference by mu and gr square. Okay. So you can do, but remember that this is only true for Reynolds number less than 0.1, but you can take it even till 1. It's not too bad. Okay, please you can do that exercise to convince that this value comes to be this. Okay. Now so for very low Reynolds number there is not much wake formation, etc. But as we increase Reynolds number, so you have film formation, again the boundary layer formation here, and so the fluid moves up, because over here you have the stagnation point. And at the stagnation point, all the kinetic energy of fluid is converted to pressure. So the pressure here is very high, so compared to pressure at other places on this surface. So fluid starts rising. It follows this surface and rises up. So in this region, you can say that del P by del X is less than 0. So it's a favorable condition. At certain point, del P by del X will become 0, and actually the pressure here will be less than pressure here. So then the flow has to separate. Once the flow separates, then you have what is known as the wake formation. Okay. Instead of flow reaching here, it just separates here. So you have sort of wake formation from both sides. Okay. So as we increase this, as we increase the Reynolds number, then this way the point where this flow separates, it kee't moving up, and at large Reynolds number you have the flow separation that happens at 85 degree or so. So when the boundary layer flow is still remains laminar. There is no eddies or sort of those kind of things here. Boundary layer remains laminar, but you have wake formations here. Okay, but here because of wake formation, etc., you will have again some turbulent eddies, etc. But the flow associated with this surface is still laminar. So at those conditions, the wake region can be seen as symmetrical sort of. So it can be seen of this. Now, since the wake region is large at this instant, the contribution from pressure is drag is dominant, so to say. Not what's it's significant, but it's dominant. Major contribution to the total drag actually comes from this pressure drag, because of the large wake formations, and this happens at large Reynolds number, like a log 10⁵ or so. Now, when the flow, if you increase the Reynolds number further, the flow in the boundary layer itself becomes turbulent, and you have so that actually delays the So now if you increase the Reynolds number further, or further, your flow in the boundary layer itself becomes turbulent, and because of that, it actually remains attached to the surface for much longer, and then the separation gets delayed, and so now your wake region becomes smaller, and this actually results in sudden, so now your pressure drag significantly reduces suddenly because of this transition. Pressure drag is significantly. So this results in decrease of overall drag as well, because your film drag is whatever it is. It has increased a little, but this since major contributions from the pressure drag, this becomes so drag actually comes down. Okay, and this you can see in this correlation. So typically, similar to what we had for friction factors for flow through straight tubes, we also have the similar thing for this sphere, and similar graph is also available for cylinders. You can check it. This this corresponds to Stokes law, and you can see that even up to Reynolds number equals 1, there is small error, but you can use with that limitation on accuracy. In the intermediate region where you have the in the intermediate region where your pressure drag keeps increasing, but your skin friction drag or friction drag keeps reducing, your main overall effect, drag coefficient remains constant. Okay, at very close to this is where you have transition to turbulence, and at that point the drag coefficient suddenly becomes very small, because your wake becomes small, wake region becomes small. Okay, so typically this is the equation that you can use to calculate your drag. Friction factor is defined as drag by half rho square. So from here you can calculate drag will be 2f times area so 2f area so f drag should be equal to friction times area times half rho v square. So rho v naught v infinity is square. So from here you can calculate the drag force. Okay. So as you increase the velocity, the drag force of course increases with a square, but your friction coefficient reduces, and calculate the drag. Okay. So again, typical method will be you start with calculating Reynolds number first, then you read this graph to calculate friction factor, and then you calculate drag, and if you have to calculate terminal velocity, then you use the force balance to calculate terminal velocity. Right, we saw that earlier as well. Okay, so with that, just note that you have similar graph available for other curved surfaces like cylinders or discs and so on. With that, let us do some simple problem. So let's say a ball, seamless ball, in this case for simplicity, is thrown twice in air without any swing or spin at 2 speeds. The property is given. So let us see which of these statements will be true. So the drag on first ball will be more, drag on first ball will be less, or both will be same. So you can go consult this graph and come back in. answer it. So let's say instead of drag, you calculate actually, you compare for drag coefficient. That is much easier to check rather than you go on calculating. You can calculate other things as well. So, but let's do the comparison for drag coefficient here. In the last one, for Reynolds number, large Reynolds number, the total drag of the order of this, the total drag has the most contribution from this, from normal forces or tangential forces. So I'm not talking about in this case about turbulent boundary layer condition. It's laminar boundary layer, but Reynolds number is very large. So that answer can be taken from what is the size of wake, for example, here. Okay. So with that, that's end of lecture 8. We'll see you again in lecture 9. So thank you for your kind attention. Okay. Goodbye.